Those two ends are connecting to the voltage measuring system. Anything that is voltage measuring system. Then whenever we are keeping this junction in hot source, okay, because of the nature of dissimilar metals, that is developing EMF. Okay, that EMF itself is giving you the voltage. Okay, fine. Then now the question is how to find out which voltage is corresponding to the which temperature. Okay, that is the question. By the sorry, by the nature, we know that ice melts at 0 degree centigrade. Okay, or otherwise, when you going towards cooling side, water freezes at 0 degree centigrade. Okay, that we know very well. That is God given. And water boils at 100 degree centigrade. Okay, that is at atmospheric pressure. Okay, that is also the great gift given by the God. Or otherwise, if it is not God, if it is the nature, okay, whatever it is, your belief. Then, whatever the voltage it is showing, when you are inserting this couple in ice, that we can assign 0 degree centigrade. That voltage represents to 0. The same couple we will be putting in the boiling water, okay, where it is readily forming the steam. Okay, then we can assume that 100 degree centigrade at particular voltage. Okay, if it is low temperature measuring thermocouple, then you will be calibrating like that. If it is high temperature measuring thermocouple, okay, so like 500 degree centigrade, 1000 degree centigrade. Anyhow, initially you can calibrate with reference of ice and water. Then for that actually many calibrating equipments are available. Okay, many calibrating equipments are available. We will be inserting this thermocouple in that calibrating equipment. Then we will be assigning. Okay, like that you can make your own thermocouple in our lab. Even many research labs are doing like that only. Purchasing this kind of readily available thermocouple is highly complicated, means expensive. Okay, that is about different. Even these thermocouples means thermometers we are using day to day life. Some are working upon infrared like this. Okay, that is okay. So sometimes when we go to the hospital, they're mentioning that 104. What is that? Fahrenheit. Okay. Then when we are seeing body temperature in another way, 34.7. Okay. Or weather temperature like 10 degrees, 18 degrees centigrade. Okay. Like different scales are available in the temperature. Okay. So major three scales are Celsius scale, Fahrenheit scale, and Kelvin scale. Okay. Apart from this, as you know, Rankine scale is also there. Okay, but those all are not using. These three scales are widely used. Okay. Celsius scale, obviously we are using 0 degree centigrade ice formation, 100 degree centigrade. Okay, water boiling. Okay, and even Fahrenheit we are not using at many places, but this is Western countries people use this. That is also as like us, like for temperature measurement of body, okay, fever measurement, or otherwise atmospheric weather measurements. These all the things only will be using. When you are going towards high temperature, like experimental combustion as well as anything at high temperatures, then we'll be measuring in case of Celsius or otherwise Kelvin. So in your class 11 and class 12, you might have practiced how to convert Fahrenheit to Celsius and Celsius to Kelvin. Okay. So Celsius to Kelvin is very easy, adding 273. Yes. So those all I am not explaining over here. Okay. And one thing is actually Kelvin Suppose when you consider Celsius scale or Fahrenheit scale, okay, so you need to go sometimes minus also. Okay, suppose see minus 5 degrees centigrade, where whether in suppose Jammu Kashmir, okay, minus 30 degrees centigrade, where whether in suppose uh, America abroad countries, okay. But in case of the Kelvin scale, it is starting from zero. Okay, it is starting from zero. That means by anyhow, by any process, okay, by any method, the temperature cannot be below 0 Kelvin. Okay, by any method or by any process, the temperature cannot reach below 0 Kelvin. Okay. That is about temperature, and even conversion and all, anyhow, you know, okay, that you please take care. This is about very basics what we have studied. What is the system? What is open system? What is closed system? What is boundary? Yes, what are the surroundings? What are the properties? Extensive properties and intensive properties. Yes. Then what is the relation between them? Okay. And what is the state? What is the quasi-static process? Yes. What is the equilibrium? Yes. These are all the things. And what are the pressure measuring equipments? What are the temperature measuring equipments? Most important thing, what is the zeroth law of thermodynamics? Okay, these all we have studied very well. This is about the chapter 1. Okay, now the thermodynamics means we will be handling one particular system. Okay, you are going to design certain system according to the laws. First law of thermodynamics, second law of thermodynamics. Okay, whatever the system we have in our hand, every system is following either first law of thermodynamics, second law of thermodynamics, or both. Okay, so how to solve the thermodynamic problems? Okay, anyhow, any problem we are solving like this only. Okay, so that is like known parameters, what you need to find out, and then you have to find out some data. This is very important thing. Okay, that anyhow, when we are solving the problems after the second chapter, okay, this is just first chapter of the introduction. After the second chapter, then you will be able to find out what are the importance of data and all, okay, and assumptions. Okay, certain assumptions are required. We cannot 100% reach close to the actual system. Okay, close to the actual system. That is only like irreversibility. Okay, and even we are assuming equilibrium, but no process is absolutely equilibrium. Yes, that we have seen earlier. Then we will be conducting the analysis. This is the manual method, or otherwise it could be certain software method. Okay. In case of thermodynamics, once you see, we'll be having many equations. That part is actually not started now. Okay. Later you will be seeing whenever you will be defining your first law of thermodynamics. Okay. There are many equations of control systems, control volume. Okay. That will be starting. Then when you are defining second law of thermodynamics and entropy, then again some more equations will be adding. Okay, and those equations will be partial differential involved with partial differential equations or differential equations. Okay, and how to solve them. Okay, all the equations, it would be complicated. Yeah. So as an engineer, a mechanical engineer or whatever, whoever are working in the thermal field, okay, so you will be facing this kind of complicated systems. Okay, in that case, hand calculations are may not be sufficient. Okay, when it is pertaining to only the equations and results are coming out to the equations, then we can use certain softwares like ES, Engineering Equation Solver. Okay, or otherwise that is up to you. If you are very strong in coding, okay, you can develop your own code by writing either MATLAB or C or C++. Okay, nowadays Python also. Okay, you can write your own code. Otherwise, there is one software, engineering equation solver. This is actually what we can say commercial kind of software, then it will be easy to feed in that instead of writing very big code in the C. Okay, if you are purely writing your code, you need to define many parameters. Okay, and then you need to define and you need to use them appropriately. Okay, but in this case, actually, that much of big procedure, whatever you are following in case of C language, that is not required. You can directly enter your equation by defining your parameters simply. Then it will be giving you answer. As like calculator, but it is for engineering equations. Okay. Yeah. So that is about engineering equation solver. Now at this stage it is not required, because first you need to know what are the equations and what are the complications involved in the solving the equations. Then only you will be knowing importance of engineering equation solver. After second chapter, okay, in couple of classes I'll be explaining this engineering equation solver. Okay, so in couple of classes are sufficient. Okay, you can learn it and even you can practice it. Okay, and even software will be given to you. Okay, and either it is cracked or is licensed. Okay, and many of you are in the institute. Okay, whoever are there in the institute, you are officially can download the ES. Okay, from CIC, and then you can install it. Okay, that is about. This is, as I have mentioned, this is only about how to solve the equations. Okay, but that solution is not sufficient. That solution sometimes is not sufficient. What you need to do, in some cases, you need a detailed analysis inside the system, what is happening. Okay, like combustion, suppose. Combustion means, suppose when you are sending certain amount of fuel and oxidizer, it is burning inside. Okay, energy is releasing and emissions are coming out. Okay, so then here, how much energy we are getting, how much energy we are losing, that calculation can be answered by first law of thermodynamics. But energy losses we will be knowing, but where we are losing the energy. Okay, then what you have to do, you have to analyze inside the process. Yes, yes, like body scanning by X-ray or CT scan. Yes, like that. In the combustor also you have to analyze. Then you have to simulate something. Okay. Then you will be knowing where flame extinction is happening or otherwise where emissions are forming. What is the reason? These all will be identified. For the complete data, you will have to run certain simulations like fluent, star CD, CFD. Okay. These are all the things. Okay. These anyhow after our third year. Okay. Whenever you are handling certain projects, whenever you are going for certain courses like CFD. Okay, there you can learn these all the things, but these all are commercial softwares, but we still have license. Okay, this is about engineering equation solver. So overall, it is not particularly relating to the engineering equation solver, even it is not particularly related to the commercial softwares like Fluid, the system analysis. Okay, so this is the overall process we will be adapting. Your objectives will be defining, and we will be synthesizing. Okay, and then analysis will be conducting. This could be engineering equation solver plus certain software analysis. Okay, along with that, you may need certain experimentations. Okay, you may need the certain experimentation. Suppose as a thermal engineer, okay, then Tata Steel kind of company is asking you to design certain burner, okay, to produce energy from their blast furnace gases. Okay, then you will be finally you have to give them in-hand product. Yes, so that means their objectives, then feasibilities, possibilities, and then initially preliminary analysis like through the governing equations by engineering equation solver, or otherwise if it is moderate complicated by hand calculations. Then after computational analysis, CFD, okay, computational fluid dynamics by ANSYS kind of software. Then Here, if you are getting some good results, then going for the construction. Construction means building the burner or fabricating the burner. Okay. Or otherwise, the same thing you can implement for internal combustion engine also. Yes. Same thing you can implement for gas turbine burner also. Same procedure you can implement for even steam uh, thermal power plant. Yes, burners in the thermal power plant. Wherever energy sources are involved. Once it is developed according to the dimensions and parameters obtained from this analysis, we will be fabricating it. Once fabrication is done, we will be testing it. Okay. Then we are evaluating it is fulfilling the objectives or not. Okay. So if we don't have this analysis part, okay, let us assume we don't have this analysis part, then objectives, synthesis, okay, and you are assuming certain thing, and then you are directly building your burner, give fuel inlets here, air inlets here, okay, exit is that side, okay, then you are building over here, and then testing, it is failing, and again going over here, do some modifications, and testing is failing, and again modification, testing going, okay, it is cumbersome actually. Then in that case, whatever the analysis we are doing, analysis itself will be telling you what is happening inside. If you are getting good results over here, obviously these all are for formality. Okay. So this is about design analysis. Okay. About any thermodynamic system. Okay. So this is about the introduction chapter. Now I am going to the second chapter. Okay. So now itself I am uploading this presentation in our Teams. Okay, I have uploaded the presentation. Can anyone please check and confirm me so that we are able to see?
Yes, sir, it's visible.
Pardon?
Yes, sir, it's visible.
Okay, okay, thank you, thank you. Okay, so now let me move to the second chapter. Okay, so can you please confirm me whether you are able to see the slide or not?
Yes, sir.
Okay, thank you, thank you. Okay, so now we are discussing very interesting topic where we are getting opportunity to define our first law of thermodynamics. Okay, so before going to define first law of thermodynamics, okay, we need to define what is work and what is energy. Okay, what is work and what is energy? Because first law of thermodynamics we have only three terms. Okay, these are obviously again overall we have only two terms: energy and work. Okay, let us see. In mechanics, you might have seen what is the work if you apply certain force upon an object, okay, and you will be able to push it for certain distance, okay, then you are simply considering the force multiplying by the distance is equal to the work. Is it? Yes, absolutely. Yes. That is in case of mechanics, okay. But in case of thermodynamics, that would be work is work anyhow, but the way of representing the thermodynamics work is different. Yes. In case of internal combustion engine, you are getting that is doing some work for you. Yes. Internal combustion engine doing work for you. What it is doing? It is carrying you from here to there. Yes, from your office to your home or your home to office. Yes, you are riding the bike. That is internal combustion engine. Yes, that is working for you. Yes, but there, yes, obviously it is moving its own weight and you from here to there. That is again moving mass from here to there. Okay, but that is the ultimate aim. But in terms of thermodynamics, it is burning certain fuel, yes, and it is generating certain energy. That energy is coming in terms of the work. Yes. What is happening in case of internal combustion engine when we have discussed in our very first class? We are injecting the fuel. Okay, since that is the compressed air, the fuel is burning. What fuel has? Fuel has chemical energy. Okay, that chemical energy or chemical potential is transforming to the heat energy. Yes, that heat energy is pushing the piston down. That is the reason the piston energy is transforming to the crankshaft. The shaft is rotating. Once shaft is rotating means that energy is transferred to your wheels. Okay, whatever those all mechanisms are there, that anyhow you will be able to see down the course. Yes, that means chemical energy is converting to heat energy. Heat energy is converting to mechanical energy. Mechanical energy is converting to the work. Okay, that means work and energy are interchangeable. Yes, the very first thing what we have to understand, work and energy are interchangeable. Yes, and there is simple example over. Okay, this ball. Okay, we are dropping over here. Yes, so and again what it is doing here, it has certain potential energy. That potential energy is changing to the kinetic energy. Yes, yes. When this ball is hitting certain thing, okay, that is generating some other kind of work. Okay, there the kinetic energy is changing to the work. Okay, so obviously, as like this example or otherwise, other example like internal combustion engine, okay, or any device, you can understand. Work is changing to the energy, energy is changing back to the work. Okay, in between, how much it is converting, how much is wasting. Yes, how much it is converting, how much it is wasting. Yeah. So because once you see your vehicle, okay, when you are burning your petrol, okay, that has 45 megajoule per kg of energy. Okay, when you calculate this 45 megajoules of energy, whether you are able to use or not, okay, but obviously you are not able to use. You will be using around half of that or 60% of that. The rest of the 40% where it is going. Yes, those are the losses. Okay, those are the losses. These are all the things. In that case, what we can define efficiency. What is the efficiency of your engine? Yes, these are all the things we are going to discuss in this particular chapter. Okay, before that, theoretically, we have mentioned that energy is interchangeable to work. Work is coming back to the energy as the interchangeable. Let us see in terms of your mechanics itself, because you all have studied your mechanics very well. Yes, see, this is an objective, okay, and certain force is applied, okay, to project it. Then initially it has velocity v1, okay, and at the location of s1. After little time, it will be reaching to the location of s2. Then it has velocity of v2. Okay, velocity is changing. Yes. Finally, the whatever the force, okay, what will be m dv by dt. Okay, these all are very basic, as you know. Yes, m dv by dt, change in velocity. Okay, Otherwise, force equal to mass into acceleration that you have seen in your class 11 and class 12, even in the mechanics part also. Okay. Then we are applying certain calculations like this, dv by ds, ds by dt. Okay. And then obviously ds by dt is again velocity. This velocity part is here. Okay. And then dv by ds. Okay. Then what are we doing over here? We are applying integration on the both sides. And what are we doing over here in mathematics? You have seen variable separable. Yes. Parameters are separating over here. Yes. And applying the integration on the both the sides and giving respective limits also. Okay. Then once you handle this part, that is becoming like variation in the kinetic energy. Yes. That means this kinetic energy equal to, this is the work. Yes. This is the very basic things you might have studied. Yes. That way, these both are interchangeable. We can understand from this. And as you know, work units we are applying certain force and we are pushing the object to certain distance. Okay. That's what's Newton meter and it is called joule. Okay. Kilojoules or megajoules, whatever it is. Okay. Now, the same way, so kinetic energy is changing to potential energy is changing back to the kinetic energy. Okay. That again changing back to the mechanical work. These are very basics. You can read yourself. Okay. And this is the thing. We can see over here how the potential energy and work are changing. Okay. And otherwise, mechanical work. See over here, we have motor over here. This is your elevator car. Okay. We will be shifting over here. Yeah, it is moving up and down. Okay. Certain electric energy is giving over here. Okay. That is doing certain potential energy this elevator car will be having. But these all are actually whatever we have seen so far. These all according to mechanics point of view. Okay. According to the particular physics point of view. In case of thermodynamics, you will not be able to see this kind of the things. Okay. So suppose this is the thermodynamics once you see, this is the battery. If it is not battery, directly electric energy is taking from the source. Okay. To tell this is the complete system, that's what battery is shown over here. Otherwise, nothing. You can directly take plug in electrical energy also. Fine. Okay. You are giving certain energy to the motor. Motor is running. Motor is connected with certain propeller or paddle wheel. Okay. This paddle wheel is inside of certain vessel. Inside the vessel, we have certain gas. Okay. We are supplying continuously certain energy. This is continuously running. Okay. So then where the energy, let us assume this chamber is well insulated. Okay. Then what will happen inside of the gas? What will happen? Temperature will be rising. Yes. Temperature will be rising. Yes. So, but here we are not lifting anything. Okay. Here we are not moving anything. Here we are not projecting any objective. Only thing is the fluid. Here we have fluid. We are stirring the fluid. Okay. We are agitating the fluid. Because of that molecular collision and all. Okay. Its temperatures are increasing. Whatever the work you are giving, that work is converting to the energy and storing here as the heat energy. Okay. Yeah, what you have to understand, thermodynamics works are like that. Even once you stop stirring this, and again once you remove this, what is this? Insulation, then this high temperature body, this is high temperature body, right? This is giving back its energy to the environment. Yes, like that. Okay. Now, here the question is both the ways. in the system we have seen, right? When we are defining the system, mass is flowing into the system, mass is going out of the system. Yes, energy is coming into the system, energy is going out of the system. That also we have to define over here, which is positive sign, which is negative sign. If you see here, what is this? This is turbine. Yes, and this is compressor. So I have written over here turbine and compressor. If I don't write, then you can understand, right, from the image itself. How this is inlet, this is outlet. What is happening over here? It is expanding. Okay, this is expanding. Because of that, work output is coming. Okay, what is the device? Such a device, when you are sending certain mass, certain high pressure, it is expanding on the device. Okay, because of that, certain work is coming. That is obviously turbine. Yes. In the first class, when we have studied a gas turbine engine, there we have seen. Here, what is happening? Certain mass is going. The mass is compressing, means pressure rising. To do this process, certain work is required. Okay, certain work is required. Work input is there here. Okay, what is this device? Compressor. This also we have seen when we are discussing about gas turbine engine. Okay, at the beginning, compressor is there, that is compressing. The compressed air is going to the combustor. Yes, there it is burning the fuel, and huge amount of energy is releasing, and it is already at high pressure. Then that high pressure, high temperature fluid, we are expanding upon the turbine. Yes, just now I have shared the presentation, right? It is there in that. Yes, so this is the turbine and this is the compressor. What is happening in case of the turbine? Work output, work coming, okay, coming out. Yes, here what is happening? Work input, work we are providing to that. That means this is the positive sign, this is the negative sign we will be considering. Okay, wherever work coming out of the system is the positive quantity, work supplying to the system is the negative quantity. Okay, that you have to remember. Okay, and here this work, okay, inexact differential we can consider this. Why? Because not only the first point and end point are not sufficient. Okay, by what process it is going, that we will have to understand. That anyhow I am going to explain after a couple of slides. Okay, now what is power? Okay, energy we know, work we know. What is power? Rate of work. Okay, rate of work. Work is joules, that you know. Joule per second is watt, that is power, that also you know. Okay, rate of work. So here, example what I would like to give you. You have one geyser in your home. Yes, that geyser is 1000 watts, suppose. Okay, then you have taken bath. Then if somebody want to go, then we have to wait for certain 5 minutes or 10 minutes. Yes, that means 1000 watts means 1000 joules per second it is giving. Okay, and your need all the time, irrespective of that, your need is 1 bucket of water. Okay, that is up to you, 2 buckets or 3 buckets or half bucket. Okay, you need some quantity of water. Yes, if you have 2000 watts, that means it is giving 2000 joules of work in a second. Okay, 2000 joules of work in a second. Then what will happen? The next person not required to wait. Why? Because while you are taking the water, when water is refilling again. Okay, that itself again continuously heating. Okay, so imagine if it is the 3000. Okay, then the volume of the chamber you can reduce, because the continuously whatever water is coming through the certain small volume, it is immediately hitting. Okay, and providing to the tap. Okay, volume of the chamber itself you can minimize. What if it is a 5000? Okay. Only thing is, obviously this is like one electric heater you have wrapped upon a pipe, small pipe. Okay, whatever water is coming in, it is getting heat and continuously coming. That is no storage matter. Yes, that means power means rate of work. Okay, that is again defined over here. Okay, now see, this is the process we are conducting over here. Okay, so because whatever the inexact differential of work, whatever is there, that we are defining. See, this is the point one, means state one, initial state, and this is the final state. Okay, certain process is going like this. Okay, certain other process also could come like this, right? Why not? Yes, like this. Or certain other process also can go like this, right? Yes, why not? Okay, certain other process can go straight away like this, right? Yes, why not? Otherwise, certain other process can come like this, right? Okay, what is happening? What is happening? See, here work we are defining in other way, which is very useful in case of the thermodynamics. In case of mechanics, what we have defined, force multiplying by the distance. Okay, here the similar thing, where the force is coming, pressure multiplying by the area. Yes, force is coming, pressure multiplying by area. Yes, actually pressure equal to force by area, right? So this is your force and dx. So at certain force is applying to compress this fluid and moving from this distance to this distance. Certain work has been done. Okay. When you are looking over here, this A multiplying by dx in case of closed cylinder. In case of closed cylinder I am telling. Yes. In case of closed cylinder, this A multiplying by dx, obviously volume change. Okay. That means PV. Okay. PV, what it is giving? Work. Okay. PV giving you work. Here we are applying integral because from 1 to 2. Okay. From 1 to 2. That's what. This is P1 V1. This is P2 V2. Integral we are applying because it is going certain different ways with the limits. Okay. And again, here we are just representing over here. This is the measured data. This is the curve fit data. That means what? Whether we are following the equilibrium or not. Okay. We are quasi equilibrium. We are assuming that we have already seen in the previous class. Okay. This is that. What is the PV representing? Okay. The PV representing area under this PV curve. This is what? This is the pressure. This is the volume. The initially your system is here. Okay, or otherwise here. Okay, then after applying certain amount of the work, this is moving like this particular path or process. Okay, and reached over here. This area under this PV curve is giving you work. Okay, it is giving you work. Let us see over here. When you are reaching from 1 to 2, you have different thoughts, obviously. That depends upon your process here. Okay, that depends upon your process here. If you are moving through this process, this A, then obviously your work is this. Okay. And if you are moving through process B, this much of strip of the work is increased. Yes, this much of work is increased. So those are just what we are saying. This is the process, that is the process. Okay, it can come this process, that can. Let us see what are the different processes over here. Okay, suppose see constant pressure process. Okay, constant pressure process, that is isobaric process we can call. Iso means same, bar means anyhow pressure. Okay, pressure maintaining constant. Okay, volume is changing but pressure maintaining constant. In that case, once you do this integration for this PdV by applying the limits of V1 V2, since P is constant, P is coming out. Okay, then it is simply V2 minus V1. This will be giving you, wherever the process is there, isobaric process, work done is P delta V. Okay, then constant volume process. Okay, constant volume process. In case of constant volume process, by maintaining the volume constant, pressure is changing over here. Okay, so boundaries are not moving at all. Okay, boundaries are not moving at all. In that case, the work is zero over here. And we have another process here, that is the curve like this. Okay, this is the curve like this. When we can get this kind of curve, both P and V both are changing. Here if you see volume changing, here if you see pressure changing. Here pressure constant, here volume constant. Here nothing constant. P and V both are changing. But however, P multiplying by V is constant anywhere. Okay, that rule it is following. That process is isothermal process. Okay, PV equal to constant means isothermal process, means maintaining the temperature of the substance is constant. That means when you are compressing, obviously pressure is increasing. Once pressure is increasing means what will happen? Temperature also increases, but still you have to maintain temperature as the constant. Then what you have to do? Continuously certain amount of energy you have to subtract from this. Okay, energy we have to subtract from this. Otherwise, we can say we have to cool it. Cool it means whatever the fluid is circulating upon the cylinder, that is taking away the energy. Yes, that is isothermal process. When you follow isothermal process, again it is the small derivation. For any derivation, the basic is this thing only. Work equal to integral PdV with the limits of V1, V2. Okay. Then we are considering PV equal to constant. That means PV equal to P1, V1 equal to P2, V2 equal to constant. Okay. Then we are assuming this. Then we are substituting over here. Okay. Because this P is varying, right? We are making P1, V1 as the constant. That way we have changed our boundaries. Yes. And then here it is completely dV by V. Then once you apply integration, this is the log function. Okay. This is the formula. Okay. Calculation of work when piston cylinder is moving by following this law PB equal to constant. That process we can call it as isothermal process. Okay. Then we can take it as the formula P1 V1 log V2 by V1. And there is another process. Okay. P V power n equal to constant. Okay. P V power n equal to constant. The same procedure we are following. This is the basic formula. And then we are taking P power n equal to P1 V1 power n equal to P2 V2 power n equal to constant. That way we have taken this parameter and we are substituting over here. Okay. Okay. And P1 V1 are initial conditions, so we have taken it out. And again V only V part is coming in the integration. Okay, we have conducted our integration and our formula is changing like this, either this one or this one or this one. Okay, this process actually we can call it as polytropic process. PV equal to constant we have called isothermal process. PV power n equal to constant we can call it as polytropic process. In this also there is one thing, PV power 1.4 means n value is 1.4. Okay, when n value is 1.4, okay, that process we have assigned a name, that is adiabatic process or isentropic process. Okay, this anyhow this process also we will be seeing in the later stage. Okay, if it is PV power 1.4, then we can take it as adiabatic process or isentropic process. Okay. Then these all variations and how the curves are changing, that is represented over here. Okay, this is about the work. Like that way, different works also there. Okay, so just one slide I have. Let me discuss this slide. Then rest of that let's discuss tomorrow. This is like, again, it is mechanics point of view. You have a solid bar. Okay, how much of work we have to apply to elongate it. Okay, there you have to apply. This is what? Stress. Okay, this is stress. And here this is a soap bubble film is formed over here. That soap bubble film you are trying to extend up to this position. Okay, there what is coming in the picture? Surface tension is coming in the picture. Okay, it has surface tension. That is the reason it is able to form the bubble. Okay, or otherwise film. Okay, like that. These are different, just for understanding only, but these are the things we don't have much role anywhere. Okay, then from the understanding of energy and first law of thermodynamics, let us see tomorrow's class. Okay. I have one request. Actually, tomorrow is Sankranti for us. In case of Tamil, we usually call it as Pongal. Yeah, and tomorrow actually that is the first day of the festival. Okay, so I would like to request you all, can we postpone tomorrow's class to some other day? Because even many Telugu students also there, even many Tamil students also there, many Karnataka students, many. So I'll compensate. Tomorrow actually we have 2 hours class. Okay. The first day means, as you all know, that we will be celebrating with certain bonfire and all. Okay. That is fun for kids. Okay. And even that is the first day of the festival. We have a class at morning. So that me and my family will be missing that. As you know, this is the big festival for us. Okay. So with your permission, so I would like to take these 2 compensation classes some other time. Is it okay?
Okay, sir.
Yes, sir.
Okay. Thank you. Thanks a lot. Thanks a lot. And who all are celebrating this Sankranti also? Okay. So enjoy your Sankranti or Pongal. Okay. Okay. Yeah. Some other places, even Punjab also Lohri. Yeah. So enjoy your festival. Okay. Okay. Thank you. Thanks a lot. See
Sir,
you on Wednesday. Yeah, please.
Sir, isn't there a holiday tomorrow by the institute?
No. Here it is. That is actually